Okay, we are recording. This is the Module 3 Session 2 webinar, and today we're going to learn more differentiation rules. So we talked about the power rule last time, which was a more efficient way of calculating a derivative because the limit definition of a derivative isn't always the most efficient way. So tonight we're going to talk about the power rule, the product rule, the quotient rule, and then we're also going to talk about trigonometric derivatives as well. So let's get started. So the product rule is used when we have two functions that are multiplied together and can't be simplified. So if we had something like, let's say we had y equals x plus 1, x plus 2, for example, we could simplify and distribute the x plus 1 and the x plus 2 and FOIL that out and get a polynomial that we could use the power rule on. We could also use the product rule because technically we do have two functions multiplied together. So we could use either the power rule or the product rule on something like that. But in cases like this, where we have 3x squared e to the x, those two functions, there's really nothing else we can do to simplify. There's no distributing. This is as simplified as it gets. So we have two distinct functions multiplied together, so we can use the product rule. And the product rule is not saying take the derivative of each function. It's a little bit more complex than that. So we have two functions, f of x and g of x. That's just saying our two functions multiplied together. So the product rule says we have the first function times the derivative of the second, so f of x times g prime of x, plus the second function g of x times the derivative of the first function. So I have first derivative of the second plus the second derivative of the first. So that's how I do the product rule, and that's used when I take the derivative of two distinct functions multiplied together. So let's do a couple examples. So let's do the y equals 3x squared e to the x. So I have two functions multiplied together, and there's no way that I can simplify them. And even if I could simplify, I still could use the product rule. So on that last question, I can still use the product rule on that one, or I could distribute and use the power rule. So one way to keep everything organized with the product rule, and you don't have to do this, this is just a method that sometimes helps, is you can label this function f and that function g. So let me go below and say f equals 3x squared and g equals e to the x. And again, this is just to keep things organized, and you don't have to do this, it just might help. We know we're going to need f prime, and we know we're going to need g prime. So right below, I'll just say f prime equals and g prime equals. What does f prime equal? So the derivative of f. Well, if I take the 2 to the front with the 3, I get 6, and then subtract 1 from the exponent, so I end up getting 6x. What about e to the x? Well, e to the x is its own derivative, so I just get e to the x. And the nice thing about writing these this way is that the product rule says first derivative of the second plus the second derivative of the first. So what I can do, if you write it this way, is I can always cross multiply and add. So fg prime is 3x squared e to the x plus 6x e to the x. And that is y prime. So that's one benefit of writing it this way. It just helps to keep organized f and g, and then f prime and g prime. And then you can cross multiply, so f times g prime plus f prime times g. And that's our first derivative. So one common mistake that happens when we have two functions multiplied together and we're asked to take the derivative is sometimes just out of habit, we might take the derivative of the first and the second function, but that's not what the product rule says. The product rule says first derivative of the second plus the second derivative of the first. So we'll do more examples with the product rule. But first, let's talk about the quotient rule. So the quotient rule is when we're dividing two functions. So if I have, this is just saying the derivative of f of x divided by g of x. So the quotient rule says g of x f prime of x minus f of x g prime of x over g of x squared. And one way that I learned how to remember the quotient rule was written this way. I will explain in just a minute what all this means. So this is how I remembered the quotient rule. Low d high minus high d low over low squared. So low is just saying the function in the denominator. So g of x, that's low. And then d high is saying the derivative of the numerator. So that's what d high means. And then high is the function that was in the numerator, and d low is just saying the derivative of the function in the denominator. So again, you don't have to use this notation. This is just how I remembered it. And all of that is divided by low squared. So the quotient rule is used when we have two functions being divided. So let's do a couple examples of this. So I want us to find the derivative of f of x equals 9x minus 2 over x squared minus 4x. So we have a quotient, and again, there's no way that I can really simplify this in any way. We did have a couple in the last webinar that the denominator was, say, just an x squared, and we could break up the numerator and then simplify, but in this case, we can't break up a denominator. So really the easiest way to deal with finding this derivative is to use the quotient rule. So similar to the way that I wrote f and g and then f prime and g prime with the product rule, one way that helps to organize using the quotient rule is to always start with low and high. We're also going to need d low and d high. And I started with low on the left because the quotient rule says low, d high. So I always put low over on the left. And low just means what's the function that was in the denominator. It was x squared minus 4x. And high is just saying what was the function in the numerator. So 9x minus 2. What about d low? What is d low? Again, just saying the derivative of what was in the denominator. Two x minus 4, so x squared, I take the 2 to the front and subtract 1 from the exponent. And the derivative of 4x, or negative 4x, I end up with, technically there was a 1 that was here. So when I bring the 1 to the front and subtract 1 from the exponent, I end up with an x to the 0, which is just 1. So I have 2x minus 4. And what about d high? What's the derivative of the numerator? Good, just 9. The 9x, when I take the 1 to the front and subtract 1, I'm just left with 9. And the negative 2 is a constant, and the derivative of any constant goes to 0. Good. And again, kind of like the product rule, and again, you don't have to use this notation. It just helped me to remember it. The nice thing about writing it this way, where you keep low in this location and high in this location, is we can do what we did with the product rule, where I cross. So low d high. So I have, I'll just put the 9 in the front because it's a constant. So 9 times x squared minus 4x. And then high d low, I can also cross. And the difference with the quotient rule and the product rule is that the quotient rule subtracts. So then minus 9x minus 2 times 2x minus 4. And it doesn't matter what order you multiply these in, so you could have had 2x minus 4 times 9x minus 2. And then all over low squared, or the denominator, which is x squared minus 4x squared. So we have two functions being divided. So I'm thinking that I'm going to use the quotient rule. And if I write the way that I have here, write low on the left side and high on the right side, and low just means what was in the denominator and high means what was in the numerator, then I can find their derivatives and cross multiply, and then I have the quotient rule. One thing that we typically do, a good habit that we're going to need to use later when we find the derivative using the quotient rule, is a lot of times you'll notice that we simplify the numerator and not the denominator, meaning we don't need to multiply x squared minus 4x out squared, because if we were finding any discontinuities, we would want to factor the denominator anyway. And in this notation, it's already factored. So we don't change the denominator typically, but we do usually simplify the numerator. And why we do that is in future modules, we're going to be finding the critical points and points of inflection, and it's easier when the numerator is simplified. And we'll talk about that more later, but let's simplify the numerator now. Let me go to the next page. So we just found that the first derivative was 9 times x squared minus 4x minus 9x minus 2 times 2x minus 4 all over x squared minus 4x squared. So let's simplify the numerator. Well, the first term, we can just distribute the 9. So we have 9x squared minus 36x. And because we have a minus, I'm going to leave that out and I'll distribute it in the next step just so I don't lose the negative. So if I FOIL this out, I have 18x squared and then minus 36x minus 4x plus 8. All of that is over x squared minus 4x squared. And you could simplify here if you wanted to, or I'll just distribute the negative and simplify all of the x terms at once. It's completely up to you. So let me distribute the negative. So I have 9x squared minus 36x minus 18x squared plus 36x, the negative negative. And again, I have another negative negative, so plus 4x and then minus 8. All over x squared minus 4x squared. And now when I try to combine any like terms, the minus 36x and the plus 36x cancel out. And the only terms that I can combine in the numerator are the 9x squared minus 18x squared. And everything else, there's nothing else I can combine it with, so I can leave it. So let me go to the next page. So I get that the derivative is negative 9x squared plus 4x minus 8 all over x squared minus 4x and the whole thing squared. And again, simplifying the numerator will be really helpful when we get to future modules and topics. The denominator we can just leave in its factored form. It's easier to figure out where the discontinuities are if we leave it factored. I'll go back to the last page for a minute. So again, if I set up low here and high there, and then I find their derivatives, then I can cross multiply and subtract. The only difference is we subtract here. And then I have low d high minus high d low over low squared. And then I can simplify the numerator, which is what we did here. And then I finally get to the final answer. Okay. So let's find the derivative of f of x equals 2x over x minus 1, x squared plus 2x minus 5 multiplied together. So there's a couple of approaches that we could do here. I'm going to, well, what do we think? What rule do we have to use to get started with this? What do we think? Well, I have 2x divided by x minus 1 times x squared plus 2x minus 5. So I do have a quotient. So I'm thinking I'm probably going to need to use the quotient rule. Is there any other rule that we might end up needing? Good. We will need the power rule. Anything else? Good. So you could FOIL this out. So we could distribute the x and then distribute the -1. That is one option. If I didn't want to multiply that out, I don't necessarily have to. So what I could do is in the denominator, I do have a quotient. Excuse me, I don't have a quotient. I have a product. I have two functions multiplied together. So I could also use the product rule. It's completely up to you which option that you want. I'll just go through with the quotient and the product rule just to show us how it would be done. But you could also FOIL it out and that would be exactly the same final answer. So I do have a quotient. So I know I need to set up low and high. And then I'll also need d low and d high. Well, low is the function in the denominator. And again, I do want to mention again, you can distribute the x minus 1 all the way through, and then you wouldn't have to use the product rule when you calculate d low. I'm going to leave it just to show us how it would be done if we didn't distribute. Okay, and the numerator, we have 2x, and d high, or the derivative of 2x, we just get 2. D low, on the other hand, again, if we use the product rule, is a little bit more complex. So we have two functions multiplied together. So if I call this f and that g, f is x minus 1, and g is x squared plus 2x minus 5. What about f prime? What do we get? Good, we get 1. Derivative of 1x is just 1, and the minus 1 goes to 0, so I get 1. And then g prime, good, I end up getting 0 for the minus 1. So g prime, I get 2x plus 2. And the minus 5 goes to 0. So now I can cross and add the 2. So I have x minus 1 times 2x plus 2 and then plus 1 times, and I'll just leave the 1 off, plus x squared plus 2x minus 5. And that is technically times 1, and you can write the 1, we just don't need to. So finding the derivative of the denominator involved the product rule, so it was a little bit more work. Like I said before, you could have FOILed it out and then just used the power rule, but I wanted to show us how we would do something when we did have the quotient and the product rule together. Okay, so we could simplify d low, the denominator's derivative, now if you wanted to, or we can simplify it later. It doesn't matter, we'll get there. So I've got everything set up to use the quotient rule. So I have low d high minus high d low. Let me go to the next page just for a little bit more space, and I'll rewrite what we have here. So low, what was in the denominator, x minus 1 times x squared plus 2x minus 5. High, what was in the numerator, was 2x. And then d low we just found using the product rule. And we got x minus 1 times 2x plus 2 plus x squared plus 2x minus 5, technically times 1. And d high equals 2. So now we can cross. So we have 2 times x minus 1 times x squared plus 2x minus 5. And then minus high d low. So we have 2x times x minus 1 times 2x plus 2. All over low squared. Are there any questions? Okay, and simplifying the numerator. Like I said before, we usually simplify the numerator because typically what we're going to be doing is using this to figure out critical values or points of inflection. In this case, we weren't asked to do that. So we could leave it here and it would be completely correct, or we could simplify. In a case like this, where this is a pretty complex numerator, we could leave it here. Again, if we were asked to find the critical value, and that will come in future sections, we would have to simplify more. And we could here, it's just that this numerator is pretty complex, so we can leave it the way that it is. Are there any questions? I just realized part of my numerator got left off by accident. Sorry about that. This part here accidentally got left off. So I distributed, so I did 2x times x minus 1, 2x plus 2, and I didn't notice that was there. So I just added that in. Sorry for any confusion. And something like this is pretty much as complex. The derivatives can get pretty complex, but having the product rule and the quotient rule together is about as complex as it can get. We'll learn another rule next week called the chain rule, and it's another differentiation technique. So trigonometric derivatives. So just like e to the x has its derivative, all of the trigonometric functions have a derivative as well. Yes, the quotient rule, the product rule too, they're definitely challenging. That's why one of the nice benefits of kind of trying to keep things organized, like by writing low and high and keeping them separate, and then their derivatives separately, it does help to keep things a little bit more organized. And like I said, an answer that's this complex, this is as complex as, for the most part, as I can imagine that they will get, using the quotient rule and the product rule together. Okay, trigonometric derivatives. So like I said, just like e to the x, so the derivative, this isn't a trig function, but the derivative of e to the x is e to the x. It has a derivative. So do our trigonometric functions. So the derivative of sine x is cosine x, and the derivative of cosine is negative sine. The derivative of tangent is secant squared x. Derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. And the derivative of cotangent x is negative cosecant squared x. One nice thing about these is that you can always have these written down or have this table printed out, and you can always refer to it when you need to. So let's do some examples with trigonometric functions. So let's find the derivative of y equals 7 secant x tangent x. What derivative rule do we think we're going to use or that we're going to need here? Very good. I have secant x and tangent x multiplied together, and the 7 is just a constant, so it just stays where it is. So two functions multiplied together, and again, there's really no way that I can simplify this. Even if I rewrite secant and tangent in another way, it doesn't simplify. So there's really not much else I can do. So I'm going to set up the product rule. So one function is f, and the other function is g. With the product rule, it doesn't matter which one you assign where. The quotient rule does, because we have low and high, which represent the numerator and denominator. So we can't switch those, but in this case, it doesn't matter. I usually just assign the first function as f and the second function as g, but it really doesn't matter. What about the 7? Well, the 7 we could leave out at the front and just remember to distribute it through later. What I usually do with a constant is I just put it with one of the functions. So I'll put the 7 with the secant x. And that way I don't have to remember later that there was a 7 and I needed to distribute it somewhere. So I'm going to need f prime, and I'm going to need g prime. And like I said, you can always go back to the table and find the values that you need. So we need the derivative of secant, and we need the derivative of tangent. So the derivative of secant is secant x tangent x. What happens with the 7? Well, the 7 will just stay where it is, just like it would if we had 7 times x squared. The 7 stays where it is. So I have seven secant x tangent x. That's the derivative of 7 secant x. And then the derivative of tangent is secant squared x. And now I can cross the two. So I have 7, and secant x times secant squared x, I get secant to the third x. And then plus, the product rule we add, tangent x times 7 secant x tangent x. So I end up with 7 secant x tangent squared x. One thing I just want to mention really quickly, secant to the third x can also be written as secant x and the whole thing to the third, but you'd need parentheses because that's not the same thing as writing it this way. Writing it this way is saying take x to the third power rather than secant x, the whole thing to the third power. So this would just be the same thing as just taking x to the third power rather than the secant x to the third power. So I just want to make sure that we know that there is a difference between these two and this one. Oh, no problem. I remember when I was first learning the exponents, I was always wanting to write it this way, and finally someone explained to me that having the x, having the third there is just taking the x to the third, and then it helped a lot. Okay, so we have our derivative. And there's really no reason at this point to simplify anything. So, I mean, we could factor out a 7 and we could factor out a secant, but we don't need to. If we were trying to find something more in the future modules, we'll start factoring, but we don't need to factor anything. We can just leave it exactly as it is. Okay. I also want to mention, just back on notation for 1 second, that sometimes you'll see parentheses with your x, and sometimes there's no parentheses. There's really no difference in those two. There's no difference at all in those two. It's just a matter of, it depends on the question. Sometimes they'll have the parentheses with the x, and sometimes they won't. So you could have parentheses around each one of those x's if you wanted to. Okay. So I want us to find the derivative of sine x over 1 plus sine x. Okay, what rule do we think we're going to need when I'm going to take the derivative of this function? So far we have the power rule, the product rule, and the quotient rule. Well, we don't have any x squared or x to the third or x with any exponent terms. We've got the trig function, so the power rule we won't use. And we don't have two functions multiplied together, not in this form, so we won't use the product rule. What about the quotient rule? Do we think we'll use that? We will. We have two functions, one divided by the other. So the reason I'm going through all that's because sometimes when you're asked to find the derivative, half of the question is trying to figure out which rule to use where. And so it kind of helps to rule things out. So I don't need the power rule here and I don't need the product rule, but I do have a quotient. So low is just the function in the denominator, so 1 plus sine x. And high is just the function in the numerator, which is just sine x. And one thing we definitely can't do is we can't ever break apart a denominator. So I can't break this into sine x over 1 plus sine x over sine x. We can't break apart a denominator, only a numerator. So then we need the derivative of the denominator and the derivative of the numerator. Well, again, you can always go back. Way too far. Hold on. You can always go back to your table. We need the derivative of sine x. And the derivative of sine is cosine. Very good. So what is the derivative of 1 plus sine x? Well, the 1 goes to 0, and then the derivative of sine is cosine. And then again, the derivative of sine is cosine x. Good, very good. So I have low, so 1 plus sine x times cosine x, so low d high, and then minus high, so sine x cosine x, so high d low. And all of this is over low squared. And again, there's really no reason why I have a parenthesis with the sine x in the denominator, as in this parenthesis here. It just, sometimes I write them out of habit and sometimes I don't. So we wouldn't necessarily have to have the parenthesis around the x here. So you could have written it just like this. The parenthesis around the entire denominator, that is necessary because we're squaring the entire denominator. And in this case, simplifying the numerator isn't too bad. That one that we had a few questions ago was pretty complex in the numerator, so we left it. But we could simplify something like this because we just need to distribute that cosine. So let me do that. So in the numerator, we have cosine x plus sine x cosine x when I distribute that cosine, and then minus sine x cosine x all over 1 plus sine x squared. So what happens in the numerator? Okay, just 1 second. So where this came from is in the numerator. If I distribute this cosine to both terms, I have cosine x, because cosine x times 1, and then plus cosine x times sine x, or sine x times cosine x. Does that make sense? Yes. So FOIL, we just basically all we have is we only have one term, cosine x, and it gets distributed to both. So you can FOIL it to both of them, yes. So I have the cosine x times the 1, which is where this comes from. And then I have cosine x times sine x, so that's where that comes from. And the other part, that was minus high d low. No problem. And then what happens in the numerator is the sine x cosine x minus sine x cosine x, those cancel. So finally I have cosine x in the numerator over 1 plus sine x, and the whole thing in the denominator squared. So I set up low and high, so denominator and numerator, and then I find their derivatives, and then I can cross multiply. If I set up low, if I set it up this way, I can always cross multiply. And the difference is I subtract rather than add in the middle. The product rule adds. I do always have to remember that the whole thing is divided by low squared, so the denominator squared, so that's where that comes in. And typically, if it's something that's fairly easy to simplify, I would simplify the numerator, and you don't simplify the denominator because it's basically factored and we don't want to unfactor it. Yes, so sine x, cosine x, and cosine x, sine x are the same thing. So sine x, cosine x is the same thing as cosine x, sine x. It's kind of the same idea as, is 3 times 4 the same thing as 4 times 3? Yes, so we can multiply them in any order and it's okay. So in order to combine like terms, they would have to all have the same exponent. So for example, if it was, say, sine squared x cosine x, and then minus sine x cosine x or something like this, we couldn't just cancel them the way that we did before because they don't have exactly the same exponents. So we wouldn't be able to simplify that in any way. We could factor out a cosine and a sine, but we couldn't simplify really in any way here, like we could when they were sine x cosine x minus cosine x sine x. But you can multiply them in any order. So I want us to find the first and second derivative of f of x equals x plus 3 times x squared minus 3x plus 9, all over x to the third. So we're finding the first and second derivative. So the good news, well, the bad news first is that we have to find the first and second derivative, and this function looks pretty complex. We've got the product of two functions in the numerator, and we have a quotient. So in this case, rather than, because I have to find the first and second derivative, and the second derivative is the derivative of the first, I'm going to try to simplify this before even taking the derivative. So going back to the one that we did earlier, just really quickly, this one. I wanted us to do an example where we had the quotient rule and we had the product rule together. And I just wanted us to have an example like that. In this case, we could do the product rule in the numerator and using the quotient rule, but it'll get pretty complex. So another option, and we could have done this in the last example, or at least simplify the denominator if we wanted to is we could simplify. So let me simplify before I even start taking the derivative. So let me multiply out the numerator. So I can FOIL this out, or you can think of it as distributing this x to each term, and then distributing this 3 to each term. So what we would have is x to the third minus 3x squared plus 9x. That's just distributing the x. And then distribute the 3, so I have plus 3x squared minus 9x plus 27. So I FOILed out or multiplied the x all the way through and the 3 all the way through. And the nice thing here is that things start to cancel, and I have a bunch of x terms and constants with exponents, so I could use the power rule on all of those terms. And it's easier than using the product rule, which we could have also done earlier. And things cancel here. So the minus 3x squared cancels with the 3x squared. The plus 9x cancels with the minus 9x. So what I have left is x to the third plus 27. So the numerator simplifies down pretty nicely. So let me rewrite this function again. So the numerator is now x to the third plus 27 once I multiplied out everything out over x to the third. So at this point, we have a much more simplified function. We could use the quotient rule. Is there anything else that we could do to simplify that would maybe help so we didn't have to use the quotient rule? Well, we can't break up a denominator, but in this case, there's only one term in the denominator, so we can break up a numerator. So I could write this as x to the third over x to the third plus 27 over x to the third. And then the first term simplifies to just 1. And we could leave 27 over x to the third, but if we're going to be taking the derivative, it's easier if we bring that x to the third up. And what happens when we bring the x to the third up? Very good. I have 27x to the negative 3. And again, we haven't actually taken any derivatives yet. All we've done is just simplified this function so that we can actually take the derivative of it. And I do want to mention, if you went through the process of taking the derivative using the quotient rule and using the product rule in the numerator, or even if you use the quotient rule at this step, you're going to end up in exactly the same place. The only reason I simplified first is because sometimes it's easier to simplify first. And in this case, our denominator is only one term. And I noticed that since it's only one term, what I can do is simplify the numerator, and then I can break the numerator up and use the power rule, and it just makes it a little easier to work with. But either way works. So now we have to actually take the derivative, the first and the second derivative. So our function is 1 plus 27x to the negative 3. So what is our first derivative? What happens when I take the derivative of 1? Very good. So the 1 goes to 0, and I'll just write the 0. You don't need to write the 0. I'll get rid of the 0 in the next question, but just for your notes, so if you're looking back later, you'll know what happened to the 1. I take the negative 3 to the front, and then I subtract 1 from the exponent. So 27 times negative 3, I get 81, but with a negative, so negative 81. And then negative 3 minus 1, so I get negative 81x to the negative 4. So if I added 1, that's where I would get negative 2 rather than negative 4. And with the negative exponents, it's not a bad idea to write that step out. Just because you have a negative and you're subtracting 1, it's easy to accidentally add 1. So that's why I usually try to write it out, just so I don't accidentally do that. Good. Okay. So I have our first derivative. We were also asked to find the second derivative. And this is why I wanted to simplify as much as I could beforehand, because if I had something that ended up like that question we had earlier with that very complex numerator, and I was trying to take the derivative of that, it would be really challenging. So if possible, especially when I'm finding the second derivative, and even the first, if I can simplify, I try to. So second derivative, I have an x with an exponent that's a numerical value, so I can use the power rule again. So I take the negative 4 to the front with the 81, or the negative 81, and then minus 4 minus 1. So I have 324, the negative negative becomes positive, x to the negative 5. And you could if you wanted to, and you don't need to, but if you wanted to take the x to the negative 5 and move it back to the denominator, you could write this. Another way of writing the same thing is 324 over x to the 5th. You don't have to, but that's just the same thing as just moving the x back to the denominator. It's up to you. Typically, when I'm taking derivatives, I usually leave the exponents, even when they're negative. It's just easier to take derivatives that way, because I would, in this case, if I was finding the third derivative, for example, I would end up just moving that x to the 5th back to the numerator so I could take the derivative anyway. Okay. And I believe that is it. Are there any questions? Okay, so tonight we learned the product rule, the quotient rule, and trigonometric derivatives. And half of each question is trying to figure out when to use which rule. And so it's not a bad idea to write the rules down and check off which ones you wouldn't need, or when to simplify first. That's also kind of a challenge, and you could always try to simplify first. So going back again really quickly to this question, I wanted to show us an example where we have the product rule within the quotient rule. It probably would have been easier to simplify this denominator first and then just use the quotient rule. So we could have simplified first in this case. We would have ended up in the same place. Sure, of course. So let's do this example again where we can distribute the denominator and then try this question a different way. Let me erase what we have really quickly. Okay, so let's try this question a different way, where we simplify first and then use the quotient rule. So first thing I want to do, I can't simplify the numerator in any way, but I can simplify the denominator. So let me multiply out the denominator. So I have x minus 1 times x squared plus 2x minus 5. So the same idea as that last question, I have this x. It's going to get distributed to all three of these. So I have x to the third plus 2x squared minus 5x. And then the negative 1 also gets distributed all the way through. So I have minus x squared minus 2x and then plus 5. The negative negative gives me a positive. And then I can simplify anything that I can. I can combine like terms. So unlike the last one that we did, where things canceled nicely, this one doesn't necessarily work the same way. So, but I can combine. I have x to the third. That doesn't combine with anything else. And I have 2x squared minus x squared. So I'm left with x squared, 2 minus 1. So I'm just left with 1x squared. And then minus 7x plus 5. Are there any questions? Okay, so all I've done is just distribute the denominator and then simplify. So let me rewrite this question. So the same function, just more simplified. So I have 2x over x to the third plus x squared minus 7x plus 5. And this is what I'm going to take the derivative of. So now I don't have to use the product rule in the denominator because I've already distributed and simplified. So let me go to the next page. Just rewrite what we just found. Five. Okay. Just making sure I didn't lose a negative sign. Okay, so now when I set up the quotient rule, the numerator is 2x, the denominator is x to the third plus x squared minus 7x plus 5 once we simplified. And now the denominator, instead of having to use the product rule, we can just use the power rule. So we get 3x squared plus 2x minus 7, and the 5 goes to 0. And then the derivative of the numerator is just 2. And now I can cross. So I have 2 times x to the third plus x squared minus 7x plus 5 minus, so minus high d low, so minus 2x times 3x squared plus 2x minus 7, and all over low, so x to the third plus x squared minus 7x plus 5, and that whole thing squared. And simplifying this numerator is actually not nearly as complex as it was when we had to use the product rule. So we could simplify this, and we could have simplified the other. It would have just been pretty significant algebra. But in this case, we can fairly quickly distribute. So we would have 2x to the third plus 2x squared minus 14x plus 10, just from distributing that 2. And then distributing the negative 2x, so I would have minus 6x to the third minus 4x squared, and then plus 14x. So the negative negative gives us a positive. And so the minus 14x and the plus 14x cancel. And then we could combine. some of the terms. So the 2x to the third minus the 6x to the third. We get minus 4x to the third. And then we can, and I just usually mark those out once I've combined them. And then the 2x squared minus 4x squared, I get minus 2x squared. And then the only thing left at this point is the 10. And all of that is over the denominator squared. So it was much easier to simplify the numerator by simplifying first, and it avoided having to use the product rule. And either way, our last answer was much more complex than this one, and that's just because had we simplified that all the way, we would have ended up here. Our answer was more complex, so we didn't simplify it. One benefit of not simplifying first is this denominator, as it is factored. And so if we were trying to find discontinuities, it would be easier to find discontinuities in the factored form than it is in the simplified form. So that's one benefit of using the product rule. In this case, either option works. They're both the same. Are there any other questions? Okay. So have a great weekend, everyone, and I will be here next week. No problem.